When you see those huge steel structures,
Yeah.
like ships being built.
Yeah, absolutely. Big hull plates, deck sections.
Exactly. And you see those weld seams, those raised lines where the plates join.
Often pretty uneven, too.
Right. And you've probably seen someone going at them with a grinder, sparks flying everywhere.
Oh, yeah. Messy, noisy work. Looks tough.
It really does. And you always wonder, how flat do they actually get it? So this deep dive, we're looking at something different, a more precise way.
A smarter way, maybe.
That's the idea. Our mission is to check out weld seam milling machines. The promise is, getting that weld perfectly flat and clean without all the grinding drama.
Right. Moving away from brute force to precision engineering, essentially.
Exactly. We've got some interesting sources looking at how these machines work and where they're actually being used. Let's just jump right in.
Sounds good, because it really is a shift, isn't it? From that very manual, skill-heavy grinding process
Totally dependent on the operator.
to something that offers, well, a lot more control and automation. It's a different philosophy.
Yeah, the sources really hammered home the issues with grinding. The noise, the dust, getting it truly flat is, like you said, down to skill.
Yeah.
So, okay, a weld seam milling machine. What is it exactly?
Well, fundamentally, it's a portable machine tool. Specialized, obviously.
Portable, on those huge structures.
Relatively speaking, yes. Portable enough to be moved to the weld. Its job is to remove that excess weld material, the bead or reinforcement, very precisely.
Wow.
It uses a rotating milling cutter. Think of a small, purpose-built milling machine head. It shaves the metal away.
Ah, so it's actually cutting, not grinding with abrasion.
Precisely. It cuts the metal down until it's perfectly level with the steel plate around it. Leaves a flat surface.
That makes sense. One source had a good analogy, didn't it?
Yeah, it was like bringing a small, precise milling operation to the massive workpiece. Instead of lugging the steel to a giant fixed machine.
Much more practical.
Definitely. And its purpose is crystal clear.
Hmm.
Machine off the unwanted weld, sometimes even leftover bits after cutting plates, and leave a clean, flat area ready for, well, whatever's next. Paint, another structure, whatever.
Okay, so what are the key bits? What makes it tick?
Well, several key parts working together.
Mm-hmm.
First, you've got the milling head. That's the business end.
Where the cutting happens.
Right.
Mm-hmm.
It's got a powerful motor, usually with constant torque that's important, and variable speed.
Why constant torque?
So the cutter doesn't slow down or speed up unexpectedly when it hits tougher bits of weld. Gives a smooth, consistent cut. This motor drives a specialized cutter head, usually with multiple little cutting inserts, replaceable ones.
Okay, milling head. What else?
Then there's the machine body or frame.
Yeah,
It needs to be really rigid and stable. You don't want vibration messing up the cut.
but portable, you said.
Yeah, so often surprisingly lightweight materials, but engineered for stiffness. Things like dovetail guide rails built into the arm holding the cutter head help with that rigidity.
Got it. Stable but movable.
Then, maybe the most critical part for big jobs, the guidance system. How it follows the weld line accurately.
We'll definitely need to dig into that.
And finally, these things are built for high material removal. They have a lot of cutting power and can feed along the weld pretty quickly.
How much material?
The sources mentioned taking off like over 5 millimeters of weld height in a single pass on one side.
Wow. That's significant compared to grinding pass after pass.
Huge efficiency difference right there.
Okay, so you mentioned guidance. That seems absolutely key.
Hmm.
If you're working on, say, a ship's deck seam that's meters and meters long, how does this machine stay perfectly straight? You can't just eyeball that.
No, absolutely not. You need something external. The most common solution is a track system, like a portable railway line.
The track. So you lay down a track next to the weld.
Exactly. You mount a rigid or sometimes flexible track precisely parallel to the weld seam. The milling machine then rides along this track.
Okay, that makes sense.
Yeah.
How do you stick the track down onto, tons of steel? Welding it temporarily seems counterproductive.
Right. You need something non-permanent but very strong. The clever part is often using powerful, switchable, permanent magnets.
Magnets,
Oh.
of course. Switchable.
Yeah, so you position the track section, get it perfectly aligned, then flip a lever or switch, and boom, the magnets lock it firmly onto the steel plate. Very strong hold.
That sounds super practical for steel work. Quick and secure.
It is. Clamps are also an option sometimes, maybe if the surface isn't ideal for magnets or for certain track types. And for shorter welds, some machines actually have those switchable magnets built into their own base.
So they can just clamp themselves down and move a short distance without a separate track.
Kind of, yeah.
Hmm.
More for shorter sections, but it's an option.
Okay, so walk me through the process then, start to finish on a typical long weld.
All right, first step. Lay down your track section alongside the weld.
Parallel to it.
Critically important. You use measuring tools to get that alignment spot on. Then you secure the track, flip the magnets, or tighten the clamps.
Track locked down.
Then you place the milling machine onto the track. Its base will have rollers or maybe sliding guides that engage with the track profile.
Okay, it's on its rails.
Now you move the machine along the track. This can be a manual feed where the operator controls the speed, or sometimes it's an automatic feed system. As it moves, the milling head does its job, shaving off the weld.
And for those really long welds, like on a supertanker deck.
That's where leapfrogging comes in. You mill a section, maybe, say, 500 millimeters to a meter long.
Okay.
Then you stop, unlock the track section behind the machine, move it to the front, carefully align it again, lock it down, and continue milling. You just keep moving the track sections forward.
Or you move the machine onto the next pre-laid track section.
Right, or if you have enough track, you can pre-lay several sections. The key is that careful alignment each time to ensure a continuous flat surface.
Right, alignment is everything for that seamless finish.
Yeah.
So you get this very straight, guided cut. But what about the surface quality? Grinding can sometimes feel smooth, even if it's a bit wavy. Does milling leave, like obvious tool marks? Is it rough?
It's a fair question. People worry about a machined look sometimes, but the sources are pretty clear. Weld seam milling generally achieves excellent surface flatness, often much better than you can consistently get with manual grinding.
Flatter than grinding, really?
Yeah, because the machine is locked onto that rigid track, and the cutter spans a certain width. It cuts a very true, flat plane. It gets rid of the high spots and low spots common with hand grinding.
And that flatness must be important for, well, for lots of things.
Absolutely. If you need to bolt another structure onto that area, perfect flatness ensures good contact and stability. Think about mounting equipment bases on a ship deck.
Or coatings. Does it help with paint?
Definitely. A uniformly flat surface is ideal for applying protective coatings. No thin spots over high points or pooling in low spots. It leads to better corrosion protection, which is obviously huge in marine or bridge applications. Think about a bridge deck. That flatness underneath impacts how well the road surface lasts.
Okay, so flatness is a big plus.
Yeah.
What about the actual texture? Tool marks.
Yes, you will see tool marks. It's a milling process after all. But they're typically very fine, uniform lines left by the cutting inserts. It's generally described as a smooth, consistent pattern.
Smoother than grinding.
Often, yes, and definitely more consistent. Grinding can leave irregular swirls and deeper scratches depending on the disc and the operator. The milled finish is very predictable along the entire length.
And that texture is good for coatings, too.
Usually, yes. While the exact roughness, the value depends on cutter, speed, feed rate, etc., it's typically well-suited for industrial paints and coatings. That uniform, slightly textured surface provides an excellent key for the coating to grip onto. Much better adhesion.
So better adhesion means better protection, longer life. Makes sense.
Especially in those harsh environments, salt spray, weather, it can really add up in terms of maintenance savings down the line.
Okay, so we've focused a lot on ships. Naturally, they're a prime example. But these aren't just for shipbuilding, right? Where else do you find these weld seam milling machines?
No, definitely not just ships. Shipbuilding and repair are major users, for sure, but the application is broader. Essentially, any heavy industry welding thick steel plates where you need that weld bead gone and the surface perfectly flat.
Like what? Give us some other examples.
Okay, the sources point strongly to the offshore industry. Think oil and gas platforms or those massive foundations for offshore wind turbines.
Lots of heavy welding there.
Tons of it. And they need that flatness for structural integrity, for coating performance in that corrosive sea air, and just making sure huge components fit together perfectly.
Okay, offshore. What else?
Bridge construction. Milling welds on the steel decks or on the big girders. Again, it's about getting things to fit correctly, but also creating that uniform surface for paving or anti-corrosion layers. Better lifespan for the bridge.
Right, infrastructure longevity. Makes sense.
Then you have large tank and vessel fabrication. Big storage tanks for oil, chemicals, water, also pressure vessels, pipelines. Sometimes you need smooth internal welds, sometimes external. Milling helps achieve that precise profile.
Okay. Any others?
Yeah, even railway vehicle manufacturing. Milling wells on the frames and bodies of trains or rail cars, partly structural, partly even for aerodynamics sometime.
Really aerodynamics, huh?
And just generally heavy structural steelwork. Any large fabrication where you just don't want a raised weld sticking out, maybe for looks, maybe for clearance, or again for paint preparation.
So it seems the common thread is large scale, heavy steel, and a need for precision finishing on welds.
That's pretty much it. Anywhere that grinding is too slow, too messy, or just can't deliver the consistent flatness required.
Okay, great. Let's try and pull this all together then. We started with that image of grinding sparks on a ship hull.
The traditional way.
And we've explored this alternative, weld seam milling machines. If you had to boil it down, what's the main takeaway for our listeners?
I think the core message is that these machines represent a leap forward in precision and efficiency for dealing with weld reinforcement on big steel structures. They're a high-quality alternative to grinding.
And it's that guided operation, the track system, that really delivers the accuracy and flatness, isn't it?
Absolutely. That's the game changer compared to freehand grinding. It guarantees a level of consistency that's incredibly valuable in modern heavy fabrication, not just shipbuilding, but across all those industries we mentioned.
You know, it makes you think. We often see these huge industries like shipbuilding or bridge building as maybe being a bit traditional.
Maybe slow to change sometimes.
Yeah. But adopting a tool like this, focusing on such high precision for what seems like a basic task removing excess weld, it really shows a bigger trend, doesn't it, towards automation, towards precision, even in these really heavy-duty, traditionally labor-intensive fields.
It does. It challenges assumptions.
It really does.
Yes.
And it makes you wonder, what other processes that we think of as just rough and ready are actually next in line for this kind of technological step up? What other manual jobs can be transformed by specialized, precise machines? That's definitely something interesting to chew on.